everyone, hope you are doing well. I am Akshay Parmar, Assistant Professor at LJ Institute of Engineering and Technology in IT/IC department. Today we will discuss an errors. Welcome to the video tutorial series of the data communication and the computer networks. So we will discuss error in brief today. So first of all, in this video we will discuss what is error and its type. Right? So error have the mainly two types: single bit error and the burst bit error. Right? After that, if the error is happen, right, then we will discuss about the techniques. We will detect that if the error is occurred or not, right. So error detection methods have mainly four variants: VRC, LRC, CRC and checksum. In this video we will discuss some of them. In this video we will discuss some of them, right. So let's begin with what is error. So what do you mean by the term error, and when it is occurred, right. So error is a condition when the receiver information doesn't match with the sender's information, right. So whenever the sender is sending the data to the receiver, so the data or information which is sent by the sender is not matched with the receiver information, then we can say that the error is happened, right. So when the error is happening during the transmission, right. So during the transmission, digital signal suffers from the noise that can introduce an error in binary bits traveling from sender to receiver, right. So if someone is asking when the error is happened and how error is happening, so during the transmission the digital signal is suffer from the noise. That is the basic cause of the error, right. So with the effect of that noise, they can introduce an error in the binary bit that traveling from sender to receiver. That means if the sender has sent the bit 0, it may be changed to the bit 1, or if the sender has sent the bit 1, that might be or that may be at the receiver, and whenever it receives, it is changed to the 0, right. So that means 0 bit is converted to the 1, or 1 bit is converted to the 1, right. That is the effect of the error, right. So we have seen what is error. In this diagram you can see that whenever the sender is sending the data, right, that is in the sinusoidal wave, a square wave, right. So in the during the transmission, the error is suffering from the noise and the data is having the erroneous data, right. So whenever the receiver is receiving the data which is with the error only, right. So when the transmission of the digital signal take place between the two systems, such as the computer as shown in the figure, we have taken the computer 1 as a sender and computer 2 as a receiver. The get contaminated due to the addition of the noise to it, right. So that data is contaminated due to the addition of the noise during the transmission, right. So computer 2 is not receiving the data which is sent by the computer 1. It is necessary to detect and correct the error, because that errors can become serious threat to the accuracy of the digital system, right. So it is necessary to detect and correct the error, because those error can become the serious threats to the accuracy of the digital system, right. So that's why we have to detect and correct the error which is occurred or happened during the transmission, right. After that, let's see the type of the error. So there are mainly two types, as we have discussed: content error and the flow integrity error, right. The content error are nothing but error in the content of the message, as we have discussed about. For an example, 0 may be received as a 1 or vice versa. So we can say that if sender has sent the 0, it may be the receiver at the receiver end, it is received as a 1, or if the sender has sent the 1, it may be received at receiver end as a 0, right. So such errors are introduced due to the noise added into the digital signal during the transmission, right. So the content errors major cause is the addition of the noise during the transmission, right. After that, let's see the type of bit error, right. So there are the mainly two types: single bit error and the burst bit error, right? So what do you mean by the single bit error and what do you mean by the burst bit error? For the single bit error, the term single bit error is shows that it suggests that the only one bit in the given data unit, such as the byte in the error, right? So that means only the one bit can be the change from 0 to 1 or 1 to 0 as shown in figure, right? So in the figure we have taken an example about the data, right? So sender has sent the data 0 1 1 1 0 0 1 1, right? So during the transmission or in the transmission media, the noise is mixed up with this signals, and they are at the receiver end. They are receiving 0 1 1 1 0 0 1 0. Here you can observe that the last bit is changed from 1 to 0. That in that only the one bit is changed in the data. So it is called the single bit error, right? After that, let's discuss the burst bit error. If the two or more bits from the data unit, such as the byte change from the 1 to 0 or 0 to 1, then the burst error are said to have the occurred, right? The length of the burst is measured from the first corruption of the bit to the last corrupted bit, right? So the length of the burst is measured from first corrupted bit to the last corrupted bit, right? Some of the bits in between may not have been corrupted, right? Burst error are illustrated in the given figure, as you can see that, right? So in this we have sent the data 0 1 1 1 0 0 1 1, right? So during the transmission, the noise is added in the signal and mixed up with the signal, and we are getting 0 1 0 1 1 0 1. Here you can observe that there are the three bits are changed from 0 to 1 or 1 to 0 during the transmission. So we are not getting the signal which is transmitted, right? The transmitted signal was 1 0 1 1 1 0 0 1, where we are getting the signal as 0 1 0 1 1 0 0 1, right? So there are the bit different of the three bits, right? So we can say that the burst error is occurred, right? So this is about the single bit error and the burst bit error, right? So let's be the important definition about the related code. What do you mean by the code word and the code rate, right? So code word is the encoded block of bit, as already seen in the it contains the message bit and the parity or redundant bit, right? And code rate is defined as a ratio of number of message bits k to the total number of bits in the code word, right? So code rate is equal to k divided by n. Here you can observe that what is the code word? Code word is an encoded block of bit. It is already seen in the content bits, that is parity and the redundant bit, right? So data bits and the parity bits is combined called as a code word, right? And where the code rate is defined as the ratio of number of the message bit to the total number of the bit in that code word, right? So here is its equation. Code rate R is equal to k divided by n. After that, let's see the code efficiency. What do you mean by the code efficiency? The code efficiency is defined as the ratio of the message bit to the number of the transmitted bit per block. So we can say that it is the code rate only, right? So code efficiency is equal to code rate is equal to k divided by n, right? So this is the important definition about the code. And let's see the error detection method. There are mainly three methods to detect the error if it is occurred or not. Now it has a three types: VRC, LRC and the CRC. In the VRC it stands for the vertical redundancy check, LRC stand for the longitudinal redundancy check, and CRC is stand for the cyclic redundancy check. So let's see about why the error detection method is having, right? So when the code word is transmitted, one or more number of the transmitted bit will be reserved So 0 and 1 or vice versa due to the transmission impairment, right? So thus the error will be introduced. It is possible for the receiver to detect this error if the receiver code word is not one of the valid code word, right? So if it is corrupted, then it is not valid code word, so receiver can decline to accept that data, right? So when the error are introduced, the distance between the transmitted and the received code words will be the equal to the number of error as illustrated in the given figure. Here you can observe that the transmitted code words are that, right, and received code words are that. So for the first example, you can observe that we have the bit sequence, right, and at the from the transmitter side, at the receiver side, that data we are receiving. Here you can observe that in the first example only the one bit is changed, right? So 10 is changed as a double one, right? So number of the error is 1 and the distance is called the 1 because it is occurred as the first place from the beginning. In our second example, the number of the bits are changed twice, right? So 0 triple one 0 1 0 double one is changed to 0 triple one 1 0 double one. Here you can observe that the two bits are changed. One is changed to 0 and 0 is changed to 1, right? So the number of errors are 2 and the distance between that two occurrence is 2 only, right? And in the third example, we can observe that the 3 bits are erroneous. 0 is converted to 1, 0 is converted to 1 and 1 is converted to 1, right? So you can observe that the number of errors are 3 because they are the 3 bit changes in that sequence, right? And the distance of the that distance is 3 only, right? So that is about the error detection, right? Hence, to detect the error at the receiver, the valid code word should be separated by the distance of more than 1. Otherwise, the incorrect receiver's code word will become the sum other valid code words and error detection will be impossible. Let's begin with the parity. What do you mean by the parity? The simplest technique for the detecting error is add an extra bit known as the parity bit to each word being transmitted, right? As shown in the figure, generally a MSB of the 8-bit word is used as a parity bit and the remaining 7 bits are used as a data of that message. Here you can observe that the first bit is a parity bit and remaining that D0 to D6 are the data bit here, right? So mainly there are the two types of the parity, even parity and the odd parity, right? So what do you mean by the even parity and what do you mean by the odd parity? As the term describes itself, even parity means the number of ones in the given word including the parity should be the even number, right? It should be a 2, 4, 6, 8 and so on. So the number of ones including P1 to D0 is equal to even number. So we can say that it is even parity. What do you mean by the odd parity? The odd parity means the number of ones in the given word including the parity which should be an odd. The 1, 3, 5, 7 or so on, right? Let's move forward about the two-dimension check, right? So when the large number of the binary words are being transmitted or received in the succession, the result collection of the bit considered as a block of data, right, with the rows and column. The parity bits are produced for each row and column of such block of data. The two set of the parity bits are so generated are known as the longitudinal redundancy check LRC bits and the vertical redundancy check VRC bit. So right, so let's discuss about how it's working. So let's discuss about the VRC, vertical redundancy check. VRC stands for the vertical redundancy check and it is also called a simple parity check. In this technique, the redundant bit called parity bit is appended to the every data unit so that the total number of the ones in the unit including the parity become odd or even, right? So that is the basic functionality of the simple parity. There are the two type of the parity generator, even parity and the odd parity. In the even parity generator, the number of ones including the parity should be the even, and in the odd parity, the number of ones including the parity should be odd. Let's say it by one example. We have a data 00 1 00 1 1 0. Here you can count that how many ones are there. There are the 3 ones, right? So number of ones is 3. Data plus parity. If we want the even parity, so we are adding an extra 1 bit after that data, right? So we have the data plus parity bits are the sequence is 00 1 00 1 0. That is our data, and after that we are adding an additional 1 to make an even number of the ones in that sequence, right? So we are adding an extra 1 at the end. That's how we are getting the even parity, right? After that, let's see another example about the parity. Here the data is 00 1 1 0 1 1 0. The number of ones in that data sequence is 4, right? If we want even parity, so data plus parity is the data that is already available 00 1 1 0 1 1 0, and after that to make an even parity we are adding 0 because the number of ones is already 4 there. The 4 number is even number, so we don't need to add an additional 1 at the end. So we can simply add an additional 0 in the parity bit, right? So our data plus parity bit is the data plus 0 at the end, right? So that's how we can achieve the number of ones as an even number, that is 4 in our example. After that, let's see an example about if we need an odd parity, right? So data is similar 00 1 1 0 1 1 0. Here the number of ones are 4, right? So if we want an odd parity, so we need to add a 1 at the end of the data, right? So data plus parity bit is 00 1 1 0 1 1 0. That is our data, and at the end we are adding an 1. That is our parity bit to make a number of ones an odd number, right? So after adding the 1 as a parity bit, we are getting number of ones in that data sequence, but that is data plus parity is 5, right? So number of ones is 5 in the data plus parity bit, right? So that's how we are achieving the odd parity, right? In that we are adding the parity bit 1 to make a number of ones to the odd number, right? So that's how we are making an even parity and the odd parity, right? After that, even parity checking scheme. How the even parity checking scheme is working? Whenever the sender is sending the data, let's take an example about it is 00 1 0 1 1 0 1. That is the data which is sender is transmitting from the sender side, right? For an example, we have taken this data sequence, right? So that data is sent to the, after that, after getting the data, we are calculating the parity bit, right? So for the even parity checking, we need to see that if there are the number of ones is even or not, right? So if the number of ones is even, then we can add an 0 as a parity bit, and if the number of 1 in that data is odd, then we have to add an 1 as a parity bit. In our example, the number of ones is 4, so we are simply adding the 0 at the parity bit, right? After getting that parity bit, it is transmitted to the via transmission media to the receiver end, right? After the data is received by the receiver end, that is 00 1 0 1 1 0 1 and 0. That is last 0 is added as a parity bit by the system, right? After getting the data, they are counted at the receiver side, they are counting the number of ones at the receiver side, right? After getting that, they are checking that if the number of ones is even or not, right? So we are checking the even parity checking. So if the number of even is no, then we can simply reject the data because it is having the odd number of ones in the data, where we have made an even number of the number of ones in the data plus parity. So it is not the data which is sent by the transmission side, right? So we can simply reject the data. And if the number of evens ones is even in the data plus parity which is received at the receiver end is even, then we can check that we can access that data by dropping the last parity bit, and we can access the data which is sent by the sender side or the transmission side. That's how we can check about the even parity. That's about how we are checking the even parity, right? The similar kind of system or similar kind of mechanism is working for the odd parity checking also, right? So in that, the sender is want to send the data sequence, right? In our example, we have set and data sequence is 00101101, right? That is the data which is sender is want to send to the receiver end, right? So first of all, what we will do, we will calculate the parity bit, right? So in that, the number of ones is 4 because we have the 4 ones in that data sequence, and we want to add an odd parity, right? So the number of ones should be in the odd number. So we are simply adding the parity bit as a 1 to make a number of ones as an odd number, right? So we are simply adding the 1 at the last as a parity bit. So by that, the data plus parity bit is 11101010. That is our data plus the parity bit is 1, right? So that is the parity plus data bit are the bit sequence is 00101101, right? That data plus parity is transmitted through the transmission media from sender to receiver end, right? So during the transmission, if the noise is occurring or encountered, then the data might be changed or something like that, right? So in the data transmission, that one bit is changed from 1 to 0. In our example, that number of 1 is changed, right? So after receiving the data plus parity at the receiver end, they are also counting the number of ones there. They know that is the odd kind of parity checking, right? So they are seeing that the number of ones in that sequence is only 4. That is even, not an odd, right? So it will checking that if the number of ones is odd or not, right? So if the number of 1 is odd, then it is acceptable, and if the number of 1 is not odd, in our example the number of 1 is 4 here, right, at the receiver end. So we can simply reject the data, we can simply reject the data by knowing that is the no odd parity checking, right? So that bits are somewhere erroneous, we can assume that, right? So we can simply reject the data. But if the data is having the odd number of 1, then we can discard the parity bit and access the data. But in our example, the 1 bit is transmitted from 1 to 0 during the transmission due to the noise, right? So we are not seeing that the total count of ones in the data plus parity sequence, that is changed from odd to even, that is 4 in our case, right? So we can simply reject the data by that, right? After that, the drawback of the simple parity checking, the VRC can detect all single bit error. It can detect burst error only if the total number of error in the data unit is odd, right? Cannot detect the location of the error in a bit, right? So as we are seeing that if the error is happen, then we can simply detect that there are somewhere the error is happening by the calculating the number of ones in that data plus parity checking, right? But by that we cannot judge that which bit is changed during the transmission, right? So that is the limitation about the simple parity checking. So that's about the and the VRC. In our example, we have seen the errors in brief. That's all about today's video. Thank you for the watching.